Good afternoon. I'm Spot On Weather meteorologist Matthew Euler, and welcome to the How the Weather Works Part 3, How the Weather Works training series. This is the third part. In today's training, I'm going to discuss some features on upper air weather charts above the ground, those weather charts that meteorologists use above the ground, as well as the difference between two new terms, barotropic and baroclinic, and then I will get into a discussion on the jet stream. Of course, a lot of us are more familiar with the jet stream, as TV meteorologists typically point out the location of the jet stream, and it's a very important mechanism in the atmosphere that plays a large role in steering of storms, in determining what type of temperatures we have here at the ground where we live. And also in the wintertime, the jet stream can be very, very important as far as, where is the Arctic air going, where's the major storm track setting up, and so that's going to be really interesting material today. The overall picture here on the beginning of today's training, I'm showing some wispy cirrus clouds. Now, cirrus clouds are usually seen year-round, and they occur generally. They can be the blow-off. They can occur as a result of the blow-off of thunderstorms. They can be a harbinger of changes with an approaching mid-latitude storm system. They can also, cirrus clouds can also indicate the presence of the jet stream. And in this particular image, I'm showing some very wispy ice crystal cirrus clouds being stretched out by strong upper-level winds. So when you see, let me go ahead and grab my tool here. So when you see the wispy nature, see how these are really spread out, these cirrus clouds? This is indicative of the very strong upper-level winds, and that's usually in association with the jet stream nearby. So when you see like these clouds, these wispy feathery clouds spread out over larger horizontal distances, very strong winds are occurring in the upper atmosphere. Right, so let's first start today's training on talking about upper level winds, upper level pressure charts. The first term I'm going to talk about is ISO heights. And anytime you see the prefix ISO when we're talking about weather, ISO refers to equal. So ISO height is a line of equal heights. And these equal height lines are measured in a unit known as geopotential meters. And I abbreviated that GPM. These heights depict generally the overall upper level heights where air pressure remains at a predetermined constant value. So for example, if we were to look at the 540 ISO height on a 500 millibar chart, which is at about 18,000 feet above the ground, that would depict, that 540 ISO height line would depict those areas where the height of the 500 millibar pressure surface was equal to 540 decameters or 5,400 geopotential meters above mean sea level. Now, ISO heights indicate thickness of air columns from mean sea level to the pressure surface they define. Usually we reference the surface as sitting at about 1,000 millibars. And here's the big thing about air columns, and we talked about this in previous training session, I believe it was part 2. We talked about the height of air columns. Warmer air columns tend to be much taller and expand, whereas colder air columns tend to be much shorter and contract. And when we have higher heights, that generally indicates a warmer air column with greater thickness or higher thickness values, while a colder atmosphere would yield much lower ISO height lines on upper level charts, and this would be indicative of colder temperatures because with colder air columns, those air molecules are packed much more closely together, tightly packed. They tend to want to move closer to the Earth's surface when it's a cold air column, whereas a warm air column, those air molecules spread much further apart and they tend to expand. Now, of course, living in the mid-latitudes, for example, United States, or if you're watching us from Europe, you have to factor in this term called topography. And topography refers to elevated terrain. So when I talk about topography, I want you to really think about mountainous areas. Okay? So in the United States, we have the Cascade Mountains in the Pacific Northwest. We have the Sierras down in California. There is the Rocky Mountains, which extend from north to south across the western U.S., from portions of Montana down through Idaho, all the way down through Colorado, and extend a little bit further south than that even. And then we have the Appalachian Mountains of the United States, which generally extend along the eastern U.S., from northeastern Georgia all the way up into portions of Pennsylvania. So we have this air in the upper levels that's moving about, but we also have these areas of higher elevation. And when the wind blows, you get these pre-selected pressure values that, again, define the bottom of the column, let's say 1,000 millibars, and the top of the air column might be up to 500 millibar thickness. That's 18,000 feet in the atmosphere, 500 millibars. The ISO heights, or lines of equal heights, can be used to describe dynamic pressure patterns both aloft, above where we live, and also depict geostrophic winds. And as this wind blows up against this higher topography, the air masses, the pressure patterns are going to be altered. So, looking at bullet number 1 there, when I say, when we refer to these upper level winds on these upper level weather charts, a good thickness chart that I would be interested in using maybe east of the Rocky Mountains, east of the Mississippi River, may be 1,000 to 500 millibar thickness, because my 1,000 millibar surface is flatter, especially over the Midwest. Now, if I go back towards the Rocky Mountains area, a city such as Denver, which is a mile high, I may want to use an 850 millibar chart as my bottom of the air column because of the mountains and the topography. Now, just as a reminder, geostrophic winds, I talked about that in the previous training and how the weather works training series, so please take a look at that training. Again, I do an in-depth explanation about geostrophic winds and about the balancing forces involved in that, where the winds are generally going to blow parallel to these ISO heights, these lines of equal heights above the Earth's surface. That's a geostrophic wind. Now, there are generally what you expect with heights is they're going to tend to decrease or get lower. When they do, that's going to generally represent lowering air pressure, and increasing ISO heights, on the other hand, indicate rising air pressure. So we talk about areas of low pressure, we talk about areas of colder air, and those colder air columns, we're going to generally have decreasing or lowering height values as we go up in the atmosphere. Now, if we're talking about high pressure, a big upper level ridge, for example, in the upper levels of the atmosphere, that's the case where we're going to see these ISO heights actually increase with altitude. Moving on now to 2 new terms for you, and I wanted to introduce this in part 3 because I'm going to talk a little bit more about this later down the line in the How the Weather Works training series. There's a difference between the term barotropic and baroclinic. Now, I want to reference you to these 2 diagrams at the bottom of the slide that show a couple different features. The solid dark lines, the solid black lines on both images represent those ISO heights, those lines of equal height contours. And then these dashed lines tend to represent isotherms. ISO meaning equal, therms referring to temperature. So lines of equal temperature are these dashed lines in both drawings. Now, when we look at a barotropic situation here on the left, what's going on is you have the isotherms, or lines of equal temperature, basically setting up parallel to these ISO heights, okay, the dark solid lines. So you notice how these dashed lines run pretty much parallel to the solid black lines, ISO heights. That is a case in which there's no type of advection going on with the temperature. There's no intersection of these isotherms across these height contours, these ISO height lines. That indicates a barotropic state. Okay. On the other hand, on the right-hand side here, we have a case where these isotherms, lines of equal temperature, actually cross these ISO heights, these dark solid lines. Notice it right here? That's a location there. This is another location up in this area. And then I have another location, and then this location. Well, actually, it starts to become more parallel there. But in general, the dashed oval here indicates an area where we have baroclinicity, or a baroclinic situation in the atmosphere. So in general, look at the relationship between the dashed isotherms and the solid height contours, or isoheights. If they're parallel to each other, we have barotropic situation. We have no change in any type of atmospheric quantity. Okay, it's going to remain basically the same. But if we have any type of crossing of these isotherms, for example, in this graphic, we do have some sort of temperature advection going on when we see something like this in a baroclinic region. So with a baroclinic situation, just in general, we talk about in a thermal field or a temperature field with temperatures decreasing from south to north. We tend to see low pressure with isobars deepening at the center when we get that set up. So baroclinic situations, a baroclinic atmosphere favors a surface low pressure system to get stronger. When I use the word deepening, I'm referring to intensifying or getting stronger. Isobars, by the way, are those lines of equal surface barometric pressure. All right, iso again meaning equal, bars referring to those solid lines in the Earth's surface, those that represent the millibars that encircle the high and low pressure systems at the surface. So temperatures decreasing from south to north, low pressure with these isobars is going to intensify towards its center. Now if I add heat to an air column, again, it's going to cause that air column to expand and get taller. Isobars in this case are higher in the warm column than in a cold column. And this is going to cause the axis of low pressure to tilt. So from the surface low pressure center, it's going to be a tilting effect with height toward the colder air mass aloft. With high pressure centers at the surface, the overall vertical axis is going to tilt towards the warmer air mass aloft. So when we have baroclinic systems, whether they be low pressure systems at the surface or high pressure systems at the surface, we tend to get a tilting with height from these surface pressure features. Now with a barotropic situation, it's much more different. The low and high pressure centers at the surface, they possess cores of either warmer or colder air, and there's no crossing of these isobars and the isotherms. So that's right here. So we're going to talk about four different systems that are actually considered barotropic. Again, the isotherms remain parallel to these isoheights. And that's what we're talking about here in bullet number 1 of this slide. Now, first barotropic system I'm going to introduce you to is called a warm core high. And with a warm core high, anytime I mention the words warm core, I want you to think that the warmest temperatures are at the center of this pressure system. So with a warm core high, the warmest air is at the center, and there is increased air pressure approaching the center of the high to increase the isobars, or these upper level isoheights in the highest core. Colder air and lower pressure occur at the edges of this warm core high pressure system. So notice on the graphic here at the bottom, you notice how each of these solid height contour lines is in solid blue. So everywhere along this particular solid blue line is a constant pressure of 900 millibars. Everywhere along this particular solid blue height contour or iso height line has a pressure of 800 millibars and all the way up to 600 millibars, higher up in altitude in the atmosphere. But you'll notice this expanding dome-like feature with a warm core high. So the overall heights rise drastically. They get higher with altitude when we're talking about a warm core high. And they tend to lower, the upper level heights lower on the edges of warm core highs. Right? A good example of a warm core high is the Azores Bermuda subtropical high pressure system in the Atlantic Ocean. In the summertime, this is a great depiction of what it looks like from the surface into the vertical, high up in the atmosphere. It actually strengthens with height. With cold core highs, on the other hand, high pressure at the center of these systems, the cold core, any cold core system, again, just want you to think cold core, coldest temperatures are at the center of this high pressure system. Now this is reflecting the surface high pressure system. Generally, the upper level heights tend to lower, believe it or not, with height, with altitude in the atmosphere above a cold core high. So it's a very shallow system. Usually it's usually associated with very dense, shallow, cold air. And the higher aloft you go, generally you see lower heights right directly above it. In fact, to the point to where you get this red L, you get upper level low in the vertical position over a cold core high. So very shallow systems. Okay, you'll notice in general how the pressure pattern is reflected. Now, there's warmer air at the edges of a cold core high, and this does promote increasing heights despite lowering pressure at the surface. Cold core highs generally tend to weaken with height, again, possibly resulting in this low pressure area aloft. I'm going to talk about two more types of barotropic systems in the atmosphere. The first one is a warm core low, here on the left graphic. Rising heights of isobars occur, even with low pressure systems at the surface are associated with decreasing barometric pressure. But with warm core lows, with the warmest air at the center of this system, generally you get higher pressure system aloft above a warm core low. This is an example of a warm core low. Is something we're very familiar with during tropical season, hurricane season. When we get a hurricane, any tropical cyclone is actually considered a warm core barotropic low. And this is the exhaust that you want over the top of a tropical cyclone, this warm core low. You want divergence or spreading of mass aloft over this type of system, which is going to allow for ventilation. And that's going to result in increasing low-level converging air and much more rapid vertical rising air motion. And then everything's going to get fanned out again over the top. Let me see if I can draw this real quick. Let me see here. Let me try to go to the pen here. And I'm going to show you what happens with for example, a tropical cyclone or this warm core low. You have air that's flowing inward like this. Low-level converging air, okay? See how this is pointed? These arrows inward. And then as the air converges, it rises in the vertical like this, okay? And then higher above the warm core low, you have this high pressure aloft, which acts to diverge or spread out the air over the top of this thing. So if this upper level high is exceptionally strong, you get a lot more removal of mass over the top of this thing. The airflow continues to accelerate inward towards the center of this warm core low or this developing tropical system, and those upward vertical motion currents continue to intensify or get stronger. And then this system deepens and gets stronger over time, and you might go from a tropical depression to a tropical storm to a hurricane. If you're in the Western Pacific Ocean, the same type of system we call typhoons. But just wanted to show you that. All right, let me go ahead and erase that. Erase this. All right, now, on the other hand, we're going to talk also about, let me go back to this. For this graphic on the right, we're going to talk about a cold core low. Now, a cold core low intensifies with height. The upper level heights actually dip or get lower above a cold core low. Now, an example of a cold core low in the United States would be a cutoff low, especially during the wintertime, where you get a pocket of colder air aloft in this location, situated right above that cold core low. So this is usually associated with very unstable showery precipitation. You get a colder pocket of air, especially if you get daytime heating of the Earth's surface. This will tend to set off more showery precip that kind of starts and stops relatively quickly. I just wanted to show you the vertical structure of a cold core low as well. Right, so now, since you have introduction on what iso height is, what is the difference between barotropic versus baroclinic, we'll now talk about jet streams. So I want you to think about our analogy again with cold and warm columns of air. Warmer columns are going to occupy more volume, they're going to be much taller. This is going to allow those iso heights in the warm column to expand to higher altitudes than you'd see in the colder column at the same altitude. This produces a pressure gradient for us that drives air parcels from the warm column to the cold column. And then Coriolis force, which I talked about already in a previous training video. It might have been part 2 of the How the Weather Works training series. But take a look at my past videos. I talk a lot more about Coriolis force and how it acts to turn the wind to the right if it's a tended path in the northern hemisphere. Anyway, this Coriolis force is going to act on the gradient from a higher, taller column to a shorter, colder column. It results in what's known as a thermal wind. And if that gradient is strong enough, this results in a jet stream. All right, so here's some great pictures. I got 3 pictures here kind of describing jet streams. Okay. Now, I haven't gone over the global circulation or the 3-cell theory yet in this series, but just bear with me for a moment as I just basically cover it. So at the equator, we have very strongly moving vertical air motion because the equator is so warm and moist, it's hot year-round. The sun is high in the sky, it's always heating the surface very strongly at the equator. So that heated, moist air wants to be positively buoyant, it tends to rise. Okay. Notice how tall this air column is over the equator. Okay. Let me get the drawing tool out one more time. I want to show you this. Okay. All right. So if I were to look at an air column over the equator, this is how tall it could be. Now, when I get to the mid-latitudes, and by the way, the Hadley cell extends from the equator, 0 degrees latitude, to 30 degrees north latitude in our example. Okay, that's the Hadley cell. The Ferrel cell is also known as a mid-latitude cell, and that expands from 30 degrees north to 60 degrees north. And then there's the polar cell, from 60 degrees north all the way up to 90 degrees north at the North Pole. All right. So again, comparing these columns here over the equator, we have much greater heating of the column, which results in these air molecules being much further apart and expanding away from each other. There's much more volume here. Okay. Now, if I go towards the mid-latitude cell, the Ferrel cell, I want you to look at this. So see how now we're getting a shorter column at that particular point. And if I go all the way up to the polar cell, I'm much lower now, okay? This is the shortest column of air here because the air is so cold in the polar area. And as a result of this, let me see if I can do this here. Notice the slope from the top of the columns at the respective areas of latitude. So the tallest column over the equator area, then kind of like a medium-sized vertical column there at about 30 degrees north. And then up at 60 degrees north, we have the shortest column. But there's a difference in height across these 3 columns of air. Now, within the tropopause, the tropopause is simply a transition layer between our first layer of the atmosphere, the troposphere, where all our weather occurs, and the second layer of the atmosphere known as the stratosphere above it. The tropopause is that transition layer between that troposphere and stratosphere. And there's the big differences between these air columns and the temperatures between these air columns, the differences in temperature, actually result in the formation of 2 distinct jet streams for the northern hemisphere. We have the polar front jet stream, which is generally occurs around 60 degrees north latitude in conjunction with the polar front. And then we have a subtropical jet stream, which is much higher in the atmosphere, which occurs around 30 degrees north latitude. Okay. The subtropical jet is going to be much higher in altitude, usually up around 200 millibars or 40,000 feet above the ground, whereas the polar front jet, the height of this jet is going to vary depending on time of year. During the winter, the polar front jet stream is much lower in altitude because we have much colder air to work with, and that much colder air is so dense that it's a more contracted air column in the winter. Subtropical jet usually resides at 200 millibars pretty much throughout most of the year. But these are 2 very important jet streams, subtropical jet and polar jet. So now let's take a look at the image. Let me go ahead and erase that real quick. Right. Just erase all that. Okay. So now let's take a look at the graphic here in the upper right. It just kind of shows you subtropical jet stream tends to be closer to the equator. So it's further south in the northern hemisphere, around 30 degrees north latitude. And there's your polar jet stream represented by the blue arrows. And that's usually located around 60 degrees north latitude. Now again, the bottom graphic just shows you the major difference between the heights of two different columns of air. One being a warm air column, and then one being a cool air column. So there's a big difference in height, and you notice how this solid white line represents the 500 millibar height. Everywhere on this white line has a constant pressure of 500 millibars, and notice where the 500 millibar level resides, how high off the ground it is in the warm column as compared to the cool column. All right, so moving on to a further discussion on jet streams. The strength of a jet stream is going to be dependent on the temperature gradient, or those temperature differences between the polar areas and the tropical areas, and between these air columns. Greater intrusion of polar air into the middle latitudes, which usually reside between 30 and 60 degrees latitude. If you have a greater intrusion of polar air, that increases this temperature difference or gradient. It produces faster jet streams during wintertime. So jet streams are strongest during the winter season. Jet stream changes its position throughout the course of the year. As far as where the main polar front jet stream axis sets up, it's much further south in the wintertime as that temperature gradient, much colder polar and arctic air shifts from the polar areas towards the mid latitudes. So that's going to result in that polar front jet stream shifting south in the winter. And then it moves further north in summer as that temperature gradient really slackens during the summer season. Jet streams tend to exist, as I mentioned, at lower altitudes or lower elevations above the ground in wintertime as that mean or average temperature of the air column decreases. And now mountains and that topography again come into play when we talk about jet streams. Terrain actually can cause damming and redirection of air masses while different heat capacities. When I talk about a heat capacity, I'm talking about the difference in heating properties between a land surface versus a water surface. Land is going to heat up much more quickly and much more efficiently than a water surface. Overall, all these impacts, terrain and mountains, the heat capacity differences of land versus water, they all conspire to produce a meandering jet stream, looping into a wavy pattern with cold air generally situated to the left of the jet stream axis or to the north, and the warmest air is going to be to the right, or if we were to use a direction, south of the main jet axis. These contortions allow redistribution of warm air poleward and cold air equatorward. This is all about the Earth's heat budget. It's all about redistribution of heat from the tropics to the polar areas and the cooler air from the polar areas towards the tropics. So these jet streams exist to help redistribute Earth's heat budget. Tropical air masses tend to reside beneath jet stream ridges, and cold polar air masses tend to reside beneath jet stream troughs. So in general, if I were to draw, let's draw a jet stream axis. All right, it's in dark here. I probably should change that. Let me change the color on the pen. So let me erase this real quick. Okay, now let me go into pen and, whoops, let's go pen. Let me change this color to red so you can see it better. All right, so let's say this is my jet stream, okay? I'm just going to draw a jet stream out, okay? Here's the arrow indicating direction of motion from the left to the right side of the screen. Generally, this area where we have almost looks like a mountain shape, this is known as a ridge. This is, I'm just going to abbreviate it R. That's a ridge. And then this area where we have almost like a U-shaped pattern, that's known as a trough. Okay, so I'll abbreviate that with a T. Generally, beneath these ridges of the jet stream, you tend to get much warmer temperatures and you generally are much drier. Whereas in the trough, it's usually much cooler and also much more unsettled. So you usually get precipitation when you're dealing with a jet stream trough, and you get dry and mild weather, warm weather in a ridge. So I just wanted to kind of show you that. But the overall goal here is redistribution of the heat. If, let's say, this, by the way, the top of this slide here is going to be north, the bottom of this slide is going to be south. So ridges tend to pump up warm air, push warm air poleward, right, at that location in the ridges, while cooler air gets redistributed in these troughs from the polar areas to the north down into the mid latitudes. So just wanted to kind of show you the basics of a jet stream overall. All right, we're going to move on here. I'm going to erase this. Just kind of wanted to show you some diagrams here to further explain this point. Okay. Now, interestingly enough, due to global warming and decreasing temperature differences from the tropics to the poles, what's happening for global warming is, the Arctic areas, the polar areas are warming at twice the rate of the mid-latitude areas. They're warming up twice as quickly. So what does that mean? That means the Arctic areas, or those polar areas, are actually getting warmer and warmer with each passing year because of global warming. And now your temperature difference between the lower latitudes, the tropics, for example, all the way to the polar areas is getting less and less. That temperature change is getting less and less each year with global warming as the Arctic heats up twice as fast as the mid-latitude areas. What could this possibly result in? This could result in the jet stream wind speeds continuing to weaken and become, when we have a jet stream which has weaker wind speeds, the jet stream becomes more wavy due to a weaker thermal gradient. And what do I mean by the term wavy? Let me show you. All right. Here's an example of a wavy jet stream. We get a trough, we get a big ridge, we get a trough, we get a ridge, and so on. That's a wavy jet stream right there. Okay? Now, let's take a look, and I'll draw out. Let me erase this first. Oops, I'll move it here. Oops, I advanced slides. Hang on a minute. All right, so let me erase this. I'm going to show you an example of a non-wavy jet stream. Okay. All right, so let's see. This would be an example of a non-wavy jet stream, one that kind of just goes west to east like this. All right. So we're talking about with global warming that we could see more of a wavy jet stream and a weaker jet stream as far as the winds go. We also could see longer lasting blocking patterns, which may result in increased frequency of stagnant weather patterns such as hotter, drier conditions or colder, wetter conditions over the same location for longer periods of time as these upper level ridges, which are associated with the dry, hotter weather, and those upper level troughs with the jet stream with the cool, wet, and unsettled weather remain over the same locations. This diagram in the bottom right shows what a warming Arctic is doing. These gray arrows represent your jet stream axis, your polar front jet stream. And notice this is a less wavy jet stream here. In general, in normal circumstances, you have a stronger jet stream. The coldest air remains over the Arctic areas. But with global warming, what's happening is we're getting these large blocking upper level ridges with the jet stream, and we're getting these much deeper troughs with much colder air contained within them. In fact, over the last couple of years, I have really noticed uptick or increased frequency of these huge upper level ridges, especially over the North Pacific, as well as at times into the North Atlantic. And whenever you put excessively warm air up into the Arctic area through these upper level ridges, you're going to have a very deep, anomalously deep trough, which is going to usher in very frigid temperatures. And there's a phenomenon known as a polar vortex, which is associated with this. When the polar vortex is strong, it's stable, and the coldest air remains over the Arctic areas. But if the polar vortex weakens, then much colder air is allowed to move south into the United States or into Europe, into these deep upper level anomalous troughs. So again, this is something to think about as we move forward. All right, so now I want to talk about something known as ageostrophic wind and something within the jet stream axis itself that is known as a jet streak. Now, all a jet streak is an accelerated area within the jet stream axis, extremely fastly moving winds within the jet axis core. This little oval shape represents a jet streak. And I'm going to walk you through the different points here. I have 5 points on this diagram. Point 1, point 2, point 3, point 4, point 5. So at point 1, we have, now I want you to imagine too that the parcel is going to move through this jet axis, through the jet streak, and then out of the jet streak when we talk about this. So initially at point 1, the air parcel is situated in a good position. It's in geostrophic balance. This is a balance between the pressure or height gradient force from higher to lower heights and that rightward turning Coriolis force. So I used to tell my students when I taught dynamics, I used to put a smiley face right here because the air parcel is in perfect balance, geostrophic balance. Winds are blowing parallel to these iso heights. Now as the air parcel continues to move to point 2, it's beginning to move into a much faster area. By the way, this inner solid oval shape here, looks like a football, that represents 120 knots of wind speed. So the air parcel at point 2 is accelerating into this. This is known as a jet streak entrance region. Now, what happens when the air parcel accelerates is the pressure gradient or height gradient force acts to the left of the air parcel and tends to be much stronger than this rightward directed Coriolis force. So what happens is we get upper level mass to be deflected to this left rear quadrant of the jet streak. So we have excessive mass in the left rear quadrant of the jet streak. We have removal of mass in the right rear quadrant of the jet streak. Now as we continue to move along to point 3, the air parcel eventually gets back into balance. Here's my little smiley face again over here at point 3, right in the center of the jet streak. This is a condition, again, known as geostrophic balance, where we have the height gradient force directed from higher toward lower heights, acting to the left of the air parcel, and we have a completely balanced Coriolis force acting to the right of the air parcel, right in the center of the jet streak. Geostrophic balance is reestablished. Now, as the air parcel comes out here to point 4, it's going into a lower accelerated area. The speeds of the wind through this particular jet streak are starting to decrease again. The air parcel is slowing down. So as the parcel comes out of the jet streak, it's still moving fairly quickly into an area of slower wind speeds, and this is resulting in an imbalance again, ageostrophic flow or ageostrophic wind, where we have the rightward directed Coriolis force much stronger than the leftward directed pressure gradient or height gradient force. And then we get to point 5 and the air parcel is once again in balance with the surrounding atmosphere, where the height or pressure gradient force is balanced by the Coriolis force. So what happens here? All right, when the air parcel comes out of the faster area of the center of the jet streak into this slower area as it goes out of the jet streak exit region, is we have excessive mass accumulating in the right front quadrant of this jet streak, and we have removal of mass in the left front quadrant of the jet streak. By the way, this is a review of what ageostrophic wind means. Okay, it's just simply a wind above the boundary layer, which, by the way, the boundary layer in a non-mountainous area usually extends from the surface to 3,000 feet above the ground level. Right? So, ageostrophic, a wind above the boundary layer that blows at a different speed from that of the geostrophic wind predicted by the pressure gradient force. Now, let me draw this here. I want to draw this out. When you look at a jet streak overall, you want to divide it up into 4 quadrants. So, by the way, this is the center of the jet streak right here where I'm drawing the red. But you want to divide it up into 4 quadrants. So what you would do is just draw a plus. You can make a plus sign right over the top of this jet streak. Okay. This is going to be the left front quadrant of the jet streak. This is the right front quadrant. This is the left rear quadrant. And then this is the right rear quadrant. Okay. And so our 2 main forces that we're analyzing at every point as this air parcel travels through this accelerated velocity in this jet stream, this jet streak in general, we're analyzing the pressure gradient force and the Coriolis force from point 1 This is point 1, this is point 2, this is point 3, point 4, and point 5. So again, geostrophic balance, everything, the air parcel is in complete balance. Pressure gradient force or height gradient force and Coriolis force equal and opposite to one another at point 1, at point 3, and at point 5. The ageostrophic components happen at point 2 in the jet streak entrance region and at point 4 in the jet streak exit region. In the jet streak entrance region, the pressure gradient force or height gradient force is temporarily stronger, acting to the left of the air parcel, pushing excessive mass, upper level mass, over to the left rear quadrant. And then over here at point 4, as the air parcel comes out of the accelerated speed area, it's slowing down, and we have the rightward directed Coriolis force temporarily exceeding the leftward directed height gradient force or pressure gradient force. So we have an accumulation of mass in the right front quadrant and a removal of mass in the left front quadrant. So again, divide the jet streak into 4 quadrants, and we'll call that left front, left rear, and right rear quadrants. And due to ageostrophic wind flow, where the pressure gradient force or height gradient force and the Coriolis force are out of balance, we get an accumulation of mass at the jet streak entrance region into the left rear quadrant, as I stated in the previous slide. This results in sinking vertical motion. A reduction of mass occurs at the jet streak entrance region into the right rear quadrant, resulting in rising vertical motion. Due to ageostrophic wind flow, an accumulation of mass occurs at the jet streak exit region into the right front quadrant, resulting in sinking air motion. A reduction of mass occurs at the jet streak exit region into the left front quadrant, resulting in rising vertical motion. So, why is this important? Why do we analyze these jet streaks, these accelerated areas that are contained within the jet stream core? Because they result in areas of upper level convergence, upper level divergence, and they result in these direct and indirect circulations. When we live here at the Earth's surface, we only realize the weather by what's happening at the Earth's surface. But the atmosphere is you got to think of it in 3 dimensions, and that's exactly what we're doing in today's training. By the way, DIV is upper level divergence. I got the key right here. CONV represents upper level convergence. So we're at 30,000 feet above the ground in this analysis. This is another jet streak right here. You know how we have 50 knots everywhere along this solid black line, and then the wind speeds increase to 100 knots. They double in speed at the center of this jet streak. But what's important is when you, the left front quadrant, okay, that is this location here. This is left front. Okay. So I'll just abbreviate that LF. This is the right front. All right. I'm just going to divide up the quadrants again one more time, so hopefully you'll understand this. Right. Now this is the left rear. Okay. And this is the right rear. Okay. So RR. Okay. So if the air parcel is at this location here, and it's moving that way through this jet streak, accelerated area of wind speeds within the jet stream axis, you have accumulation of mass associated with this upper level convergence in the right front quadrant. See that? And then you have removal of mass because of ageostrophic flow in the left front quadrant right here. And then you have a removal of mass in the right rear quadrant, and then a gaining or addition of mass in the left rear quadrant. So, associated with this, let me see if I can draw this out. Let me try to change the color here. Okay. So, if your location is located, let's say, in the right front quadrant of a jet streak, you're going to have, I'm going to draw a blue H here. This is high pressure. This is fair weather. The same thing goes when you increase upper level convergence, you increase mass, you have downward vertical motion. It's going to be associated with nice weather and high pressure in this quadrant. So the 2 areas that have nice weather, if you were to look at a jet stream map at 300 millibars, if you were located in the right front quadrant of a jet streak or the left rear quadrant, you would have nice weather. But if you are located in the upper level divergent areas of the jet streak, which would be this area here, okay, left front quadrant and the right rear quadrant. If you're located in these two locations, then you have upper level divergence, removal of mass, ageostrophic wind flow with the jet streak, and you will have storm development in either of these two areas of the jet streak. So think sinking air right here in the convergent areas. You get upper level convergence, you get sinking air motion. When air sinks, it warms and dries out. But if you're in the divergent quadrant, many of these jet streaks, you're going to have rising air, and it's going to cool, condense, form clouds, and most likely precipitation. So that is why we really analyze. That's why we analyze this. That's why we look at this. We divide the jet streak, these accelerated regions, up into 4 quadrants. We call them left front, left rear, right rear. We looked and described how this occurs. When we talk about ageostrophic wind flow, we talk about an imbalance of forces. Things are out of balance between pressure gradient force or height gradient force and the Coriolis force. And that results in either rising vertical air motion or sinking vertical air motion. And by the way, if you get 2 of these jet streaks to basically be on top of each other, you can actually get very explosive storm development. You know, some of those East Coast, we call them East Coast bombs, where pressure drops 24 millibars in a 24-hour period, or even greater than that pressure fall. That's usually associated when we get 2 of these jet streaks to merge. So for example, if you get the left front quadrant of the polar front jet stream and the left front quadrant of the subtropical jet stream to basically lie on top of each other in the vertical, you can have extremely quick upper level divergence and removal of mass aloft and explosive rising air motion in the vertical. Very strong storm system. All right, that wraps up the training today. How the Weather Works training, series part 3. I hope you got something great out of today's training. I know we covered a couple new terms, whether we talk about jet streaks and how geostrophic balance versus ageostrophic imbalance works as air parcels move through a jet streak. And we talked about jet streams. We talked about how they form. Additionally, we talked about 4 types of barotropic systems: cold core low, warm core low, the cold core high, and I think that was it, and the warm core high. Yeah, that's right. And then we talked about the term baroclinic, what it means, if we're analyzing 2 specific meteorological parameters in the atmosphere, what we're looking for, and then a quick introduction on upper level winds. And what goes on, ISO heights, what that means, and so on. Okay, thank you so much for watching today's video. I hope you enjoyed it immensely. I do apologize. I had this thing made Thursday night, but for some reason my screensaver, it didn't save my screen right at all. It was extremely blown up and huge. So thank you for your patience. I'm going to go ahead and post this to the YouTube channel now. Thank you again, and until next time, till part 4, we'll continue on this journey together, this training journey of how the weather works. Take care, everybody, until next time, and God bless.